Good morning, everyone. Well, we are going to do our last section in chapter 9, and I know some of you just got really excited because we're going to skip 9.7, so we're going to end chapter 9 with 9.6. So you can look at 9.7 if you want to, but it's not going to be required for exams or quizzes or the homework. So just your knowledge if you want to do it. So we're going to end with vectors in space. So in the previous two sections, we looked at vectors in just 2 dimensions. Well, that's not the only way to look at vectors. You can also look at them in 3D. So the nice thing about them is that most of the properties and stuff just sort of naturally flow into that. So let's look at the unit vectors first. So we had unit vectors in 2 dimensions. So with 3 dimensions, that means there's going to be 3 numbers. So for vector I, be 1, 0, 0. Vector J, 0, 1, 0. And the third vector is going to be vector K. K hat, I'm sorry. 0, 0, 1. So for your position vector, if you have 2 points in space, so again, we're talking about space, so there's an X, a Y, and a Z. Fun stuff. Just do the same thing as what we did before. So take the X's and subtract them, same for the Y's, and then same for the Z's. And you can write them as a combination of I's, J's, and K's, or as an algebraic vector. So x2 minus x1i plus y2 minus y1j plus z2 minus z1k. Or as an algebraic vector, it's got the angle brackets on it, just like these. Just take out the I, j, and the k and put commas in between. So x2 minus x1, y2 minus y1, and z2 minus z1. Okay, example 1. Find the position vector with this initial point and that terminal point, and then write it in the form AI plus BJ plus CK. So we're just doing this thing right here. So it should be able to do a lot of math in your head. So 6 minus a negative 3 is 9. 5 minus 2 is 3. And then negative 1 minus 0 is negative 1. So minus k. All right. So many of the definitions and theorems that we looked at in the previous sections apply straight on into 3D. So I'll let you guys go over those. The only thing we kind of introduced was the unit vector. And so you can take any vector and turn it into a unit vector. So a vector that would have a length of 1. So all you do is you just take it itself and you just divide it by its own length. Okay, so example 2, find the length of that vector. So what's the magnitude? So it's still going to be the square root, and then you're still going to take the numbers involved in here. You're going to square them all. So now all 3 of them and add them up. So the 6, the 2, and the negative 2. So we get a total of 44 under the square root, and then simplify it down. So 2 root 11. Okay, example 3. So find 3v minus 2w if you have these 2 vectors. So we're going to do the same thing as what we did before. I'm going to take the 3, and I'm going to stick it next to vector v. So 4i minus 3j plus 6k, and then the negative 2, we're going to stick it next to vector w. And just make sure you're paying attention to which vector goes where. So don't always take the first vector that you see here and stick it next to the first number. Sometimes they're going to see if you're paying attention and they'll mix them up. All right, so now just distribute. And then just add up your like terms. So 16i minus 23j plus 22k. And there you go. That's all you got to do. So the last part of the section deals with the dot product. And all the way you find it, all the properties and theorems, they work exactly the same way. It's just that you have this extra pair of numbers to deal with, but that's usually not a problem. Usually. Every once in a while I find a weird multiplication thing, like 2 times 6 is 8. Like, oh, well, not today. All right, so v dot w, multiply the coefficients of the i's, so 2 and 1, and then plus, take the numbers in front of the j, so 2 and 2, and then take the numbers in front of the k's, so negative 1 and the 6. So 2 plus 4 minus 6. Well, that normally gives us 0. So there's your dot product. Well, what does this tell us? Remember, if the dot product is 0, that tells you something. It tells you that the two vectors are orthogonal. There's that fun word again. Orthogonal. Well, if they are orthogonal, that means the angle between the two vectors has to be, and everybody said, 90 degrees, because that means they're perpendicular. Okay, so that will do it again for chapter 9. We are not going to do section 9.7. You can look at it if you want to, but you don't have to. So that'll do it for chapter 9. So try the homework out and let me know if you have any questions.